So I'm here on a scorcher of a day outside the Museum of Natural History at the University of Oxford in the UK with a paleontologist, Ross Anderson, who is a expert on eukaryotes and the onset at the beginnings of life on Earth. And we've been discussing, you were just telling me before I switched on this video that one of the main problems is you're not able to find enough fossils. Explain what you mean.
Yeah, so one of the biggest challenges with this kind of research is that the fossils we're looking for are microscopic. They're not like the dinosaurs and the trilobites and the ammonites that you would normally think of. We're delving back way into Earth's history here to look at how life went from being microbial to being macroscopic. And what that means is that the fossils are quite rare. They're cellular remains. They're totally soft. And so we have to go to the right rocks where the chemical parameters are such that you get these exquisitely preserved cellular fossils that we can find to tell life's history.
And tell us what a eukaryote is and the difference between a prokaryote and a eukaryote. And you were just telling me that a eukaryote really is complex life.
Yeah, exactly. So if you think about all of the life on the planet, we've got single-celled bacteria and archaea. These are kind of more simple life forms. Their DNA is throughout the whole cell, whereas eukaryotes are more complex life. They have a nucleus where the DNA is enclosed, but they also have other compartments in their cells, the mitochondrion, for instance, that allows energy-intensive lifestyles. And it's the eukaryotes which have developed complex multicellularity and macroscopic forms. So all the animals and plants that we see around the world, the fungi, those are all eukaryotic organisms.
And when did the animal kingdom split from the plant kingdom?
So animals evolved. We know the oldest fossils of animals are around 575 million years old. You can find them in the UK, in Leicestershire, but also in Newfoundland, in Canada. And those animals are already big, they're already macroscopic, so it's likely animals had a little bit of a longer history than that, but perhaps to 600, 700 million years ago.
And what's missing? Is it money? Is it a lack of fossils that we're never going to find? I mean, is there a treasure trove of fossils out there that we haven't yet discovered?
Yeah,
go ahead.
So the biggest challenge at the moment is we have undersampled fossil record. We don't have enough fossils to tell this story of this big transition. And so one of the big changes over the last few years has been we've started to understand what types of rocks preserve these exquisite fossils. And by doing that, we're going to have a much better handle on where to go look. So we're not going to look at random anymore. We're going to be able to look much more specifically. That's the rock we're going to focus on. And hopefully we'll be more successful at finding these fossils into the future.
So let's take an overview from 30,000 feet. Are we any closer now about answering the big questions about how life first evolved here? And that may not be the first evolution of life, may not the RNA and DNA sequencing, not sequencing, but development, may not be your bailiwick right now. But, as a paleontologist, I'm sure you have an interest. Are we any closer to understanding any of this than we were 20 years ago or 50 years ago?
Yeah, so the building behind us here, the University's Natural History Museum, dates to the mid-1800s, about the time Darwin was writing The Origin of Species. And back then, it really was thought that the fossil record ended in the Cambrian and that the first 90% of Earth history was really devoid of life. There were no fossils. In the last 70 years, we've made huge strides. We now find fossil bacteria going back 3.5 billion years. We can find evidence of eukaryotes going back 1.7 billion years. And we can find evidence of algae 1 billion years ago, animals 570 million years ago. So we've made huge strides as we've started to figure out which are the right rocks to find early fossils, because that's starting to give us the data with which we can record history. Just like paleontologists hundreds of years ago were looking for dinosaurs, we can now find these early life forms as well.
And given all your field work in looking for this early life, how does that make you look at the work that's being done by the rovers on Mars in trying to find microfossils or evidence for
Yeah.
past life?
Yeah, so the rovers that are on Mars are essentially small geology labs on that surface, taking the kind of measurements that we can take on our own planet. And what's great is that they're landing in places where we think the conditions are right to preserve early life forms had they been there. So we'll see what happens, but it's exciting times for planetary exploration as well.
Ross Anderson, thank you so much for your time today. We look forward to hearing more from your future research.
Thank you.